This is chapter 10, number 64, and we have a cylinder that's going around and around by a motor. It's having a lot of fun. The problem is that there's some torque of friction going on, so friction torque. Um, so, in order for the motor to completely counter the torque of friction so that it'll keep going at this angular angular velocity, we want to find out how to make them. They should be equal, essentially. So the torque of the motor. Come on, come on, come on. There it goes. Torque of the motor. Keep it going at a steady angular velocity has to be equal to the torque of friction. What that means is their angular accelerations are the same. Already the moments of inertia are the same. It's the same object. It's the same object. So we don't really care about the inertia. But the angular acceleration that's created by the motor to equal the angular acceleration that or deceleration caused by the friction, the angular deceleration caused by friction. So it's just in the opposite direction, right? It's countering it. So, question is, what is the angular deceleration of friction? Once we know that, we can make this equal. All right. Well, we know that it decelerates. Well, we know what its deceleration is actually based off of the information they gave us. It's essentially 23.9. You do the whole number, of course. This is 0. 0 minus 23.9 over 16 seconds. You plug the numbers in, you get, what do you get? Oh, I was looking at the wrong one. There it is. 1.4922561 radians per second squared. The moment of inertia for a cylinder is 1/2 mr squared. And that comes out to 3327.5 kilogram meter squared. I know it's kilogram meter squared because mass is measured in kilograms and radius is measured in meters, and it's squared, radius is squared, so that's meter squared. Okay. So, the torque caused by friction is I alpha. That equals 4965.3537 meters. Now, let's find the power, because the power is going to be the same. So Or you could put it this way. The power that's necessary to keep it at 3.8 revolutions is the exact same torque in the opposite direction times angular velocity. When you do that, you get 118,556.402 watts. It's watts. Now we need to change that to horsepower, so horsepower 746 watts. That's a 7. So divide this by 746. This is a 6, not a G. And you get 158.922791 horsepower. Sig figs. Well, let's have looks like 1 2 1 2 1 2. So we can say it's 160.